There are hundreds of billions of planets hiding in our galaxy. Yet the confirmed count of 97 worlds feels impossibly small. We search for a second Earth, but the silence is overwhelming. Are we truly alone? The year is 1995, and the idea of planets existing beyond our solar system is still purely theoretical. We had no direct evidence, no confirmed sightings, just a silent star-filled sky that offered no answers. Then in that same year, everything changed with the announcement of 51 Pegasi b, a colossal Jupiter-like world orbiting a sun-like star a mere 50 light-years away, as confirmed by NASA. This was the first crack in the cosmic wall, forcing scientists to acknowledge that our solar system was not the unique blueprint we had assumed. It was a humbling realization, and it kicked off a frantic search that would rapidly transform into a golden age of discovery. But the real revolution was still years away, waiting for a dedicated sentinel to join the quest. That sentinel arrived in 2009 with the launch of the Kepler space telescope, a mission so ambitious it would stare unblinkingly at a single patch of sky. Kepler monitored over 150,000 stars, watching for the telltale, minuscule dimming of their light caused by a planet crossing in front of them, an event known as a transit. It was a cosmic census, and the results, announced by NASA in 2018, were staggering, completely overturning every previous estimate of how common planets might be. Suddenly, they weren't an exception, they were the rule. The statistical groundwork was being laid, but we still hadn't found the one thing we truly dreamed of. A world that looked like home. That milestone was reached in 2014 when NASA announced the discovery of Kepler 186f, a planet with a radius strikingly similar to Earth's, situated firmly within the habitable zone of its cool red dwarf star. This was not a giant gas world or a scorched rock. This was the first true Earth-sized planet where liquid water, the key ingredient for life as we know it, could potentially exist on its surface. It was a potent symbol, a name that fueled countless headlines and imaginations, representing a profound shift in perspective. The statistical possibility of other Earths was no longer just a concept. Here was a tangible, confirming example. So, after all this incredible work, a question that would have seemed absurd only a few decades earlier suddenly feels urgent. Exactly how many of these worlds are we talking about? According to the NASA Exoplanet Archive, as of March 2024, 5,597 exoplanets scattered across 4,159 different planetary systems. It's a number that feels immense, a testament to human ingenuity, but it represents only the tiniest fraction of what's out there. To grasp the bigger picture, consider this. Astronomers estimate our Milky Way galaxy alone could be home to 100 billion stars. And with NASA's data from 2013 suggesting at least one planet for every star, we are looking at the possibility of hundreds of billions of worlds. This catalogue of 5,597 is not the whole story. It's just the first fleeting page in an encyclopedia we've only just begun to read, setting the stage for the entire hunt for a second Earth. In February 2017, a team led by astronomer Michael Gillon published a discovery in the journal Nature that would forever change how we picture our galactic neighborhood. They had found not one, not two, but 7 rocky planets orbiting a single dim star known as TRAPPIST-1, a system located roughly 40 light-years away. Just 2 decades prior, we knew of no planets beyond our own solar system, and now we were staring at a family of 7 potential worlds. This system is remarkable because all 7 of these planets are roughly Earth-sized or smaller, and several of them sit within what astronomers call the habitable zone, the region where liquid water could exist on a rocky surface. Unlike the gas giants that dominate our own solar system, these are solid, terrestrial worlds, and NASA's observations suggest that at least some of them could harbor oceans. The sheer density of potentially habitable real estate in one compact system was something science fiction had never even dared to predict. The standout member of this family is TRAPPIST-1e, a planet that initial observations suggest has a mass, radius, and density strikingly similar to our own Earth. This planetary twin has become a leading candidate in the search for life beyond our own world, precisely because its physical characteristics align so closely with what we know supports biology here at home. It's not just a vague Earth-like blob, it's a geologically plausible analog to our own planet. What makes TRAPPIST-1e even more compelling is the energy it receives from its star, which is remarkably close to the amount of energy Earth receives from the Sun. This places it squarely in the habitable zone, not just on the edge, meaning conditions on its surface could be surprisingly temperate, perhaps even allowing for stable bodies of water. The star it orbits is a small, cool red dwarf, so the planet is packed tightly in its orbit, but the energy balance somehow feels almost familiar. Its neighbor, TRAPPIST-1d, offers another tantalizing possibility. Models suggest it could be a true ocean world covered entirely by a liquid water ocean hundreds of kilometers deep, far deeper than anything found on Earth. While this sounds like a paradise, such a deep ocean would mean pressures at the seafloor that would challenge any Earth-like life form. But the sheer presence of that much water is astonishing. Given the type of star and the chemistry of these worlds, the sky on TRAPPIST-1e would not be the familiar blue we see from Earth. Scientists suggest that complex organic compounds called tholin could exist in its atmosphere, giving the sky a permanent orange or red hue, a stark and beautiful contrast to the world we know. If you could stand on its surface, you'd not only be on another Earth, but in an alien landscape with a sky so different it would feel like a dream. In 2019, a team of astronomers pointed their instruments at a distant world and nearly gasped at what they saw. The data coming back from K2-18b indicated water vapor in its atmosphere, a result so unexpected it forced them to completely rethink their assumptions about this type of exoplanet. The discovery, published in Nature Astronomy that year, suggested that a massive gaseous world might actually harbor liquid water, turning a once theoretical idea into a tangible possibility. Let's put the sheer distance into perspective. K2-18b sits about 120 light-years away from us, a gap so vast that the light we detect from it today actually left the planet back in 1903. That was the very year the Wright brothers managed their first brief flight at Kitty Hawk, a time when humanity had barely conquered the skies of our own world, let alone dreamed of probing the atmospheres of others. What kind of place is this, exactly? For starters, it's nothing like the rocky planets we grew up with in our own solar system. K2-18b has a mass roughly 8.6 times that of Earth and a radius about 2.6 times larger, placing it firmly in a category astronomers call a sub-Neptune. This is a type of world that doesn't exist in our cosmic neighborhood, a mysterious middle ground between a rocky Earth and a gas giant, and we know very little about what they are actually made of. Then came September 2023, and the James Webb Space Telescope delivered something that made the scientific community sit up straight. Its data pointed to the possibility of a liquid water ocean on K2-18b, but that wasn't the real headline. A detection of dimethyl sulfide, or DMS, appeared in the planet's atmosphere, and on Earth this molecule is produced almost exclusively by living organisms, primarily marine phytoplankton. Pause for a second and think about what that means. We are talking about a molecule that, as far as we know, is a byproduct of biological life, floating in the air of a world hundreds of trillions of miles away. But here is where scientists have to pump the brakes and stay cautious. A potential biosignature is not the same as proof of life, and this tentative finding demands rigorous verification before anyone can make a bold claim. So what do we do with this tantalizing clue? The answer is that K2-18b now stands as one of the most compelling candidates for a second Earth, even if it looks completely alien to us. The punchline we are left with is a question that hangs in the air. If that DMS signal is confirmed, are we looking at the first evidence of life beyond our solar system, floating in the sky of a world we can only see as a faint point of light? In 2016, a team led by Guillem Anglada Escudé published a finding in the journal Nature that immediately sparked a global conversation about a second Earth sitting right in our cosmic backyard. The announcement of Proxima Centauri b sent a ripple of excitement through the scientific community and the wider public, because this wasn't a world thousands of light-years away in some distant corner of the sky. This was a planet orbiting the closest star to our Sun, a neighbor so near that it felt almost within reach, and the implications of that proximity were staggering to consider. The discovery didn't just add another entry to a catalogue of exoplanets, it fundamentally shifted the terms of the debate about our place in the universe. Proxima Centauri b, the nearest known planet to our own, sits just 4.24 light-years from us, a distance that translates to roughly 40 trillion kilometers when you actually try to wrap your head around the scale involved. To put that in perspective, that is a journey so immense that even the fastest object we have ever built would take tens of thousands of years to complete. And yet, in cosmic terms, this is essentially stepping out your front door. Despite its proximity, the planet itself is a world of stark contrasts and profound strangeness, a place that feels both familiar and utterly alien at the same time. It is a rocky world with a size comparable to Earth's, but that is where the similarities to our own comfortable home seem to end. It orbits a dim red dwarf star, a much smaller and cooler object than our Sun, and it does so on an incredibly tight leash. This close orbit means that Proxima Centauri b completes a full revolution around its star in just 11.2 days, which means a year on this planet lasts just over a single week here on Earth. Can you imagine celebrating a birthday every single week, or having a calendar that barely lasts a fortnight? The consequences of being so close to its star are dramatic, and they point to a reality that is fundamentally different from anything we experience on our own planet. Climate models of Proxima Centauri b suggest that if it has any water, the world is likely tidally locked, meaning one hemisphere is forever turned towards its sun while the other side is plunged into an eternal, unchanging night. One side of the planet would bake in a perpetual, unrelenting daylight, while the opposite side would be locked in a frozen darkness that has never known the sun's warmth. The Terminator Zone, the thin band between day and night, might be the only place where conditions are even remotely temperate, a sliver of perpetual twilight running around the entire globe. This creates a world of extremes, a place where you wouldn't find a pleasant afternoon but rather a sharp division between an endless furnace and a never-ending winter, a concept that stretches our imagination to its limits. Yet, the star that creates this strange, static world also offers a tantalizing possibility for life over a timescale that dwarfs anything we can conceive of on Earth. Proxima Centauri is a red dwarf with a lifespan reaching into the trillions of years, a staggering contrast to our own Sun, which is only about halfway through its 10 billion-year life. This immense longevity provides a nearly unimaginable window of opportunity for life to arise and evolve, a cosmic cradle that would exist long after our own sun has expanded into a red giant and consumed the inner planets. The star's age and stability offer a crucial advantage. Time itself is the most valuable resource for evolution, and Proxima Centauri has it in near infinite abundance. Even if life on such a world is slow to develop, it would have an almost eternal canvas on which to paint its own unique biological story. A thought that is both humbling and awe-inspiring when we consider our own comparatively brief existence. PSOJ 31522 is a rogue planet, a world that drifts through the interstellar void without any parent star to call its own. Discovered in 2013, this lonely giant, with a mass similar to Jupiter's, wanders through the darkness, illuminated only by the faint glow of distant stars. Imagine a planet condemned to an eternity of cold, silent travel, a testament to the chaotic and often violent processes that shape our galaxy. For a long time, astronomers believed that planets needed a star to form, but this outlaw challenges that very assumption, suggesting that worlds can be born free and remain alone forever. In 2012, astronomers using data from the Kepler Space Telescope made a discovery that ignited the public's imagination, a world they dubbed a super-Earth diamond. The planet, named 55 Cancri E, was described in media reports as a massive cosmic jewel, sparking a frenzy of headlines about the potential for extraterrestrial wealth. The story was irresistible, a planet made of precious gems sitting just 40 light-years away, a tantalizing possibility for future space miners. It was a narrative that captured the headlines for weeks, even as the scientific community urged caution about the crystal-clear assumptions. The hype was a fascinating glimpse into how we project our own earthly desires onto the cosmos. The reality of 55 Cancri E is far more complex, as research suggests it could indeed contain a significant amount of carbon, potentially in the form of diamond. This super-Earth, with a radius roughly twice that of our own planet, orbits its star so closely that a year lasts a mere 18 hours, making it a world of extremes. The surface temperature is scorching, far too hot for life as we know it, yet the very idea of a diamond planet persists. This raises a thought-provoking question. What is a planet, and what does its composition mean for the possibility of life beyond our solar system? If a world can be forged from carbon, what other strange and wonderful configurations might exist out there? Consider for a moment the sheer scale of the space between these celestial bodies, a distance so vast it defies human comprehension. If we were to shrink our sun down to the size of a basketball, the nearest star, Proxima Centauri, would still be over 4,200 kilometers away, roughly the distance from Hanoi to Jakarta. This comparison, from a National Geographic feature, puts the immense emptiness of our galaxy into perspective, highlighting why interstellar travel is such a monumental challenge. The spaces between stars are not just empty, they are a barrier of unimaginable scale that separates us from even our closest cosmic neighbors. This forces us to ask, if planets can be cast out into the darkness and others can be made of diamond, what other surprises are lurking in the uncharted territories of space? Can life, as we understand it, truly only exist on a planet like our own, or could it adapt to the most bizarre of environments? The rogue planets, the diamond worlds, and the scorching super-Earths all point to a universe far more diverse than we ever imagined. Makes you wonder, what strange and wonderful forms of existence are we yet to find in the most unexpected of places? We talk about visiting these worlds as if it were a matter of boarding a ship and setting sail. The reality is far more humbling. Voyager 1, the most distant human-made object, has traveled about 24 billion kilometers as of 2023, a staggering distance by earthly standards. Yet that journey represents less than 1,000th of the path to Proxima Centauri b, our nearest known neighbor. So how do we grasp distances that dwarf anything we experience? Let's break it down based on NASA's own method. First, remember that light travels at about 300,000 kilometers per second. Second, 1 light year converts to 9.46 trillion kilometers. Third, multiply the number of light years by that figure to get the distance. For instance, 4.24 light years times 9.46 trillion gives you roughly 40 trillion kilometers. Finally, compare that to the 384,400 kilometers to the moon, and the scale becomes almost incomprehensible. Even our fastest technology seems pathetic against this backdrop. The Parker Solar Probe, the quickest spacecraft we've ever built, reaches about 700,000 kilometers per hour. At that incredible speed, a trip to Proxima Centauri b would still take roughly 6,300 years. Think about that number for a moment. It's more time than separates us from the invention of writing. New Horizons, the probe that gave us our first close-up of Pluto, offers an even more sobering perspective. As one of the fastest objects ever launched, it would still need about 78,000 years to arrive at our neighboring planet. That's not a journey, it's an epoch, longer than the entire history of modern humans. But speed isn't the only wall we hit. The fuel required for such a voyage defies anything we can produce, and the human body, fragile as it is, simply wasn't built for generations in deep space. The silence, the radiation, the sheer isolation would break most of us long before the stars grew closer. So, we are left with a paradox. We have found countless worlds, some with oceans and skies that mimic our own, yet we stand here, rooted to our own pale blue dot. Are we truly condemned to only look, forever wondering what waits on those distant shores? The James Webb Space Telescope, launched on December 25, 2021, did not just open a new window on the cosmos, it kicked the old one in, fundamentally changing how we observe the early universe and the atmospheres of distant worlds. Instead of just looking at a planet's size and orbit, we can now effectively read its chemical fingerprint from 120 light-years away. To understand how this works, imagine a planet passing directly in front of its star, an event known as a transit. When this happens, a tiny fraction of the star's light filters through the planet's atmosphere. By comparing the starlight before the transit with the starlight during it, astronomers can see which specific colors of light have been absorbed by the gases in that atmosphere. Those dark lines in the spectrum are a unique barcode for molecules like water, methane, and oxygen, a technique called transmission spectroscopy. The power here is staggering, since it means we can search for signs of life without ever leaving our own solar system. But this isn't just a theoretical exercise, and the telescope is already delivering results that would have seemed like science fiction just a decade ago. For instance, Webb has the capability to analyze the atmospheres of exoplanets by studying the light that passes through them, a technique that allows it to search for the signatures of water, methane, and other gases vital to life as we know it. This precise chemical analysis is our best tool for moving beyond simple classifications and asking the most profound question: is there someone out there? But what if our current methods are too narrow, and we are looking for the wrong kind of life? This is where the ambitious, almost audacious, plans for the future come in, pushing us to think beyond just peering through a telescope. One project, Breakthrough Starshot, proposes to do the unthinkable, physically send a probe to Proxima Centauri b. The idea involves using powerful lasers to accelerate a tiny gram-scale sail to a speed of 20% the speed of light, a journey that would take just 20 years to reach our closest stellar neighbor. Reaching out and touching another world is one thing, but we also need a clear logic for what we are looking for once we get there, and distinguishing between a habitable world and one with confirmed life is a critical nuance. The first step is to check the planet's size and mass to see if it could be a rocky world like our own, rather than a gas giant. Next, you must determine if its orbit places it within the habitable zone of its star, where temperatures allow liquid water to exist on the surface. Then you analyze its atmosphere for biosignature gases, those chemicals like oxygen or dimethyl sulfide that are normally produced by living organisms. Finally, the search isn't static. You have to observe the atmosphere over time to see if there are fluctuations that suggest biological cycles, like the seasonal changes we have on Earth. While the search for an Earth 2.0 continues, Webb is also broadening its gaze to investigate planets with hydrogen-rich atmospheres, which are very different from our own world but could still harbor life. This approach ensures that our hunt for life is not limited by our own biology, and that we are prepared for the unexpected, whether we are traveling to a distant star or simply turning our telescopes to the sky. We began with a question that feels almost too big to hold. Are we alone? We have searched for a second Earth, from the rocky siblings of TRAPPIST-1 to the hazy, ocean-covered world of K2-18b, and even to our nearest neighbor Proxima Centauri b, a planet that circles a dim red star in just over a week. We have imagined rogue planets drifting in eternal darkness and diamond worlds sparkling 40 light-years away. And yet, after all this searching, the universe around us remains profoundly, unsettlingly silent. This silence has a name, and it was first articulated by a physicist over lunch in 1950. Enrico Fermi, during a casual conversation, looked up at the vastness and famously asked, "Where is everybody?" That simple question, recorded by the New York Times, cut through all our assumptions and gave birth to the Fermi Paradox. It is a stark challenge. The numbers tell us the cosmos should be teeming with life, so where is the evidence? The paradox only deepens when we consider the timeline. Our universe is roughly 13.8 billion years old, and our Milky Way galaxy has existed for about 13.6 billion of those years. That is an almost incomprehensible span, enough time for countless advanced civilizations to have risen, expanded across the stars, and left their mark on the galaxy for us to find. Yet they have not. This is where the rare Earth hypothesis offers a quiet counterpoint to our hopes. It suggests that complex, multicellular life like ours might be the product of an extraordinarily unlikely chain of cosmic accidents. It argues that we may owe our existence to a stable moon that calms our planet's tilt, and to the slow, grinding dance of plate tectonics that recycles our atmosphere. Perhaps the reason for the silence is not that life is common and fragile, but that worlds like ours are almost impossibly rare. As we look toward the future, and as telescopes like the James Webb Space Telescope peer deeper into the atmospheres of distant worlds, we are edging closer to an answer. We might find that other Earths are everywhere, or we might find that our pale blue dot is a lone, precious miracle in the dark. In the end, the question returns to us. When we finally listen, will we hear an answer, or only the echo of our own lonely voice?